Okay, it's just a quick review of the part two for exam one. Overall, each of you did really well, and I'm really pleased with the way that you drew your kinetic analysis and set it up. Just a couple of details, and a couple of things that I want to mention going forward, how to even get ready for the final exam or things that we're trying to pick up through the rest of the semester. All right, so the first question was to identify the forces acting on the swimmer and then do the equation motion for horizontal. And I did I'm looking at the test on another window here, and then also for the vertical direction. All right, so just about each of you got this part correct. First, you identified gravity, which is perfect. Almost all our situations that we're going to be dealing with will have gravity as a force acting on it. Then you identified buoyancy, and those do not have to be the same points, all right? Those same application point even. I'm going to draw it over here just so it's easier to see. Now, we do know, since the person is not sinking, that these two forces are going to be equal in magnitude and opposite in direction. That's not Newton's third law. So I'm going to try to draw them at equal lengths. And this would be the center of gravity when we draw the force of gravity acting on the person. And this point here would be the center of buoyancy. They don't have to be the same place, okay, the same point. All right, so that's our vertical direction. And let's see, how do I want to do this? I'll do it over here. I'll do vertical. Equation of motion, sum of forces in the vertical direction equals MACOM, center mass, in the vertical direction. And in this case, we're using up as positive and forward motion is positive, our reference frame. So we would have our equation, buoyancy force would be positive plus negative force of gravity equals MACOMV. That's our equation of motion. And as long as the person's not sinking initially, this acceleration will be zero as long as these forces are equal in magnitude. They don't always have to be equal in magnitude. We could be submerged and have a bigger buoyancy force than the force of gravity, and that would propel the person upwards. And likewise, we could have a greater FG versus buoyancy force if we're really dealing with an object, thinking more of an object starting at the surface, and the gravity force is greater than the buoyancy force, that object would sink. And that would be some negative acceleration starting at initial velocity of zero. Okay, so there are different problems that we can work through. I don't do a lot with sinking or floating objects, so we won't really be touching too much on the vertical forces in swimming. But when we do talk about wetsuits during triathlon, one of the benefits is the buoyancy force that it provides to the person. And that in one case is a safety issue, but the other case, it actually helps with horizontal motion. And I'll explain that now. All right, and in the horizontal direction, we have a propelling force. And if I'm doing a free body diagram, I can still draw the propelling force acting at the center of gravity because, or center of gravity and center of mass is the same thing. I don't know if I have a video on that yet for this class, but these are the two same things. And there's only one really crazy situation where they're not the same point. Maybe I'll challenge you to think about what that might be. But center of gravity, center of mass, same point. So I could have put center of mass here or center of gravity, either one. So I don't know. I always do center of mass in the equation. And for whatever reason, just old habit, I use center of gravity when I'm drawing things out. Okay, so sorry, I don't mean to make that more confusing than it has to be. All right, where was it? Okay, I'm going to draw the propelling force. And I could draw it at the center of mass or center of gravity. That's technically correct, and that's technically how we do a free body diagram. In fact, we do a free body diagram more like this, where all the forces are acting on the center of gravity. we would have a propelling force, a force of gravity. And it just gets messy when you start having multiple forces acting in the same direction on the center mass. So I tend to draw it here at the hand, giving that concept that the propulsion is largely coming from the upper body. Now, what some of you did is actually drew a propelling force for the legs, and that's perfectly correct. Nothing wrong with that. But it's easier in physics to combine some of the forces. And in this case, I would combine all those propelling forces into a single force. Right? Now, we know from some research that in a typical distance swim, you'll only get maybe 10% of propulsion from the legs. But I'll tell you that when we've done experiments where we're measuring what I'm going to draw next, which would be the drag resistance force, when we're measuring this force, I would tend to draw it at the head, F drag resistance. And I think I've called this in the notes, F propulsion, F drag, because it's still drag force, propulsion. Okay. All right. When we're trying to do an experiment where we're measuring this here, what we actually do is we cheat a little bit. And we said we have the swimmer not use his or her legs for kicking. So we have them hold on to a pull buoy of some sort. And that just simplifies this physics in that because we can ultimately measure the drag resistance force by determining the drag propulsion force. And if you've watched the video where I have where we did the work in Mallorca, Spain, and the MAD system, active drag measurement device, as we do this experiment, the swimmer swims and in essence grabs a force platform that's submerged in the water. And then we can measure that propulsion force of the person pushing on the force platform and that force platform pushing back on the person, which is this force right here. And as we'll see in a second here, our horizontal equation of motion, sum of forces acting in the horizontal direction equals MACOM horizontal. And in this case, the way I've reduced it to two forces and forward is positive, I'll do propulsion force as positive plus drag resistance equals MACOMH. So what we do in our experiment is we have the person run with swim with constant velocity. We can actually measure the velocity too, but we have them try to swim with nearly constant velocity, and therefore A is 0 meters per second squared. That wipes this part out. And then our drag propulsion is equal to the drag resistance magnitude force. They're just in opposite directions, not Newton's third law. So by measuring what's happening at the hand, we're actually determining the resistance force. And the system can also determine acceleration, so you can actually quantify this part, but we always give them subjects instructions to stay nearly constant, and that just simplifies some of the math as we go forward. All right, so a question on the exam, final exam, we would see is we would be working with this, and then we would start looking at, well, how do we swim faster? Or how do we reduce the energetic cost of swimming? Well, we want to reduce this resistance force as much as possible. How do we reduce that resistance force? All right, well, 1/2 rho C d A V squared. That's our equation for that force. And we would just look at these parameters and say, what can we do to reduce these parameters? Then we could also talk about increasing the velocity by increasing the propulsion force, and that's through training or technique. We improve those two things, we're improving the ability to create a propulsion force. And that combination of things will actually help us swim faster. Okay, so that was swimming. So I thought you folks did good on that. Just an easy way to simplify this is to put all the propulsion forces into one force vector. Okay, that was the first question. The next question was on cycling. And this is cycling up some hill. Okay. And it goes out, it doesn't end there. Maybe it's something like that. That's okay. All right, what forces are acting on the system? And it's just important to remember that we're dealing with the system here as opposed to just the rider. If we're dealing with the rider, then we're looking at the points of contact the rider has with the bike. But in this case, I start with the system, and that's the bike rider. So really, I could reduce this to just a box on a ramp. Okay, it's the same thing. But we've got a fancy stick figure here to work with. What forces are acting on the system? And this is the one that is going to be really important right now that I want to talk about. The other force, and this is force of gravity. The other forces you all identified, my pen keeps drying out here. The ground reaction force at the front wheel, the ground reaction force at the rear wheel, the rolling resistance of the front wheel, the rolling resistance of the rear wheel. And most of you drew your drag force up here, drag resistance force. And then the final one is a propelling force. Okay. So this is the one that I really want to spend time. Now, some of you did draw in a bearing, and I've done that as well, a bearing resistance. And that's okay. That's good to do. A lot of times what references will do will combine these two into one resistance force, which would be rolling resistance and bearing. And I know I've been inconsistent with how I presented this in the notes, because sometimes I include this, sometimes I don't. But collectively, what I often do is I just identify all the resistance forces that I need to account for in my equation of motion. And then I also do propulsion forces and go from there. And so sometimes we'll combine all three of these into one resistance force. Okay, but the one I want to talk about right now is this one right here, the gravitational force. We can't leave this alone when we want to do our equations of motion. And really the equations of motion are going to be relative to the reference frame that's set at an angle. Okay, no longer a reference frame set with the horizontal or level. We want this reference frame because the person's going uphill. And we want to understand how to bike faster uphill, or how to go faster downhill, either way. And so we got to rotate this reference frame so that we have a parallel component. I'll use two vertical lines, and a perpendicular component, and that's perpendicular to the surface. All right, so all we need to do is decompose this force vector into these two components, because this force vector is not relative now to this reference frame. And it's easy to do. What we do is we, in essence, draw a box around the force vector, the resultant force vector, and then this component, or this side of the box that's perpendicular, hopefully I did that well, that is perpendicular to the surface is our normal force, or F perpendicular. And then the one that's parallel to the surface, that's, oh boy, that's a terrible arrow. That's an arrow. Parallel is the other component of the gravitational force. And we know if we add this vector and this vector, we get the resultant vector here. So it's all just math. A squared plus B squared equals C squared. All right, so we need to decompose this force when we do our equations of motion. I'm gonna get a new pen because those are running out. And what did I do here for the test? I did equations of motion for parallel and normal. Okay, well, okay, so in the normal direction, some of the forces acting in the normal direction, the perpendicular, equals MACOM of the system in that same dimension. And so what do we have? We have FGRF at the rear, this could be at the front wheel, at the rear wheel, front wheel plus FGRF, gee, boy, I have a hard time writing, FGRF rear wheel and minus Fn, and those are all the vertical forces, excuse me, the normal forces, okay? I put those in the equation and I get MACOM in the normal direction. Now, I'm not talking about moving uphill. I'm talking about moving relative to the surface. And in this case, the system is not moving in the normal direction. So all these forces will add up to zero because velocity will be zero, will be constant and zero. It's 0, 0, 0, 0, therefore acceleration will be zero. Okay, so that's our resistance forces in the normal direction. And I'm gonna have to get some new markers. In the parallel dimension, this is an interesting dimension. I mean, this is where we want to spend some time on. We'll have sum of forces in the parallel direction equals MACOM in the parallel direction, so moving in this dimension. Now we have to add up all our parallel forces, and I'm going to do it down here. I'll put my red one better be okay. F bearing. Okay, now that's going to be pointing opposite to the direction of motion. This direction of motion is going to be positive in this direction. Okay, so F bearing is negative plus rolling resistance from the front wheel plus rolling resistance of the rear wheel. What else do we have here? Plus negative drag, air resistance, plus parallel component, which is going to be negative, plus propulsion force. I think I got them all. Propulsion, rolling resistance, rear, front. I put bearing in, drag, and parallel. I got them all. Okay, good. All those, and I'm leaving that as positive, equals MACOM in the parallel dimension. So moving in this dimension. All right, that's our equation of motion. Now, what we end up doing is trying to understand how to bike faster uphill. And the one force I want to draw your attention to, because I'll follow up on this as we go through the semester, is this force right here. The propulsion force, which is acting in the parallel dimension. What factors influence that propulsion force? Oh, wait a second. Sorry. I'm off there. What factors influence that? It's going to be training. Okay. Sorry, that's an easy one. This is the one that I meant to highlight right here. This one right here. What factors will influence the parallel component of this force? What determines the magnitude of this force? Well, what determines it is how big this force vector is and the angle of the hill that we're going up. Those are the two things that determine it. The steeper the hill, the greater that component. The lower the hill, the less that component. In fact, if we go on the level, there's no parallel component, right? That does not exist. If we go straight up a hill, now that parallel component is equal to the magnitude of the force of gravity, which is the weight of this system, right? And obviously the steeper the hill then, that component keeps getting bigger and bigger and bigger. If I start adding heavier components, I use, heavier gear. If I weigh more, that's going to increase this force vector right here. And for any given hill, that will increase the parallel component of the force due to gravity. So down the road, I'll ask you a question like, well, how, and I would call this slope force. And this applies for running too, same thing in running. But I typically do it with cycling just because it's a little easier to decompose and think about. So what influences that slope force is the angle of the hill and the magnitude of the force of the system weight. Okay, the bigger that will be for a given hill. For a given weight, the bigger the hill, the bigger the parallel component. And obviously that's going to be a resistance force, and that's going to contribute to the kinematics of cycling uphill. Okay, so hopefully that helps to review. I thought you folks did a really great job on each of these, just a couple of little details, but we can continue to work with this, and I'm really pleased with how it went. Thanks, everyone.